VLSos here. This is a video lesson on using the power rule for taking a derivative. The derivative is the same thing as an instantaneous rate of change function, or we could call it a slope function, a function to determine the slopes of tangent lines to a curve at any point. A familiar function that we have worked with many times, f of x is equal to x squared. And we have used this in examples where we have found, through the process of finding an instantaneous rate of change, that a function for the instantaneous rate of change of x squared is 2x. We've also approached this as an analysis of looking at the curve of x squared and determining what the slope to that curve, the tangent line to the curve, is at points, and graphing those and connecting them to make the familiar linear equation 2x. Now, we're going to think of this as a power function and use the power rule, which will find the derivative or the instantaneous rate of change function for all powers. And that power rule is any power b to the n, where we're trying to find the derivative, so we put it in parentheses with this tick mark that we read prime, so this would be b to the n prime. And what we mean by that is the derivative of b to the n is equal to, as a general property, n times b to the n minus 1. And what does this mean? It means that if we're given a power, then we can take the exponent, move it down in front as a coefficient now that multiplies the power, and then we also reduce the exponent by 1. This is a property to find the derivative of any power. Notice that the derivative that we already knew, 2x, is this property in action. We bring the 2 in front, that now multiplies the power, but we've taken 1 away from the exponent. We don't show x to the 1 because an exponent of 1 doesn't change the value of the term or the base. So 1 could be drawn there, but it comes from reducing the power of 2 by 1. Let's give another example. If we have a g function equal to x cubed, then we can find the slope function, or the derivative of g, with the power rule by bringing the 3 down in front as a coefficient and reducing the exponent by 1. Quick and easy. We could use the definition of the derivative, which is a much more tedious calculation, to confirm that, and we will next lesson. But using the power rule is fast. Let's give some more special cases. If we define h of x as a power that already has a coefficient in front of it, like 2x to the 10th, then we can find the derivative of h with the same rule. The exponent is 10. If we bring that out in front and multiply, the 2's already there, so it's 2 times 10, which is 20, multiplies the same power, but we reduce the exponent from 10 to 9. Another example. What about exponents that are not integers, like 1/2? Power rule still applies. I can find the derivative of m, or m prime of x, by bringing the exponent of 1/2 in front to multiply and reducing the exponent by 1. So what's the new exponent? We start with the old 1/2, subtract 1, and get a negative 1/2. You can do that. It works. Now, it might be worth saying that to raise something to the half power is the same thing as the square root. And in this derivative expression, we have 1/2 times x to the negative 1/2. So we still have a 1/2 power combined with a negative exponent, which means the whole thing can be placed in the denominator. You take the reciprocal of the base and multiply by half at the same time. You get 1 over 2, that's the 1/2, times the square root of x, which is x to the 1/2, but in the denominator because it's negative. A little more practice. I'm going to define the n function as x to the -2. We know that we can deal with integer exponents, fractional exponents. Well, what happens if your exponent's already negative? No issue. We can still apply the power rule to find the derivative. We put the -2 out in front as a coefficient, and we reduce the exponent by 1. 1 less than -2 is -3. Be careful that you don't go the other way. How about last function, something very unusual, x to the 0. What if 0 is our exponent? If we apply the power rule, let's see what happens. The derivative of p then is bringing the old exponent out in front to multiply, and then we reduce the exponent by 1. 0 minus 1 is -1. And we can simplify this. The x to the -1 with power properties would be 1 over x. But if we're multiplying by 0, it doesn't matter what x to the -1 is, anything times 0 is 0. X to the 0 started as 1. So really we're asking if p is the same thing, p of x is the same thing as 1, then the derivative of 1 is 0. And in fact, we have a general property that the derivative of any constant is equal to 0. But we arrive at this property of derivatives, that the derivative of any constant is 0, through the power rule. And this should make sense. Visualize a constant function and think, what is the rate of change of a constant function? Constant function doesn't change, so the rate of change is literally calculated to be 0. And this example here is a property of derivatives that we want to remember because very often we're asked to find the derivative of the square root of x. And using the power property in this case to take the derivative means that it's always going to be 1 over 2 radical x. Remembered as a property, it's very useful.